Right, okay, so on to question 4, nice Born-Haber cycle to do. Lots of information there. First thing we need to do is to explain why the second ionisation energy of calcium is more exothermic than the first ionisation of calcium. Let's just have a think about it. So the first ionisation energy is that. The second ionisation energy relates to that equation. So this one is more endothermic than this one. It takes more energy to remove this electron. Why is that? Well, if you have a think about it, you're going to have the same number of protons attracting fewer electrons. This because I've already lost an electron in there. So you've got same number of protons attracting fewer electrons, therefore stronger nuclear attraction. But the next one, why is the second electron affinity positive? So it's going to be O minus gas plus an electron becoming O2 minus gas. Why is that positive? It takes energy to do that. That's endothermic. Well, if you have a look at this bit, I think it's quite clear. I'm adding a negative electron to a negative ion. So I've got to overcome the repulsion between those two negative species. So I have to put energy in to put an electron onto that because I've got to overcome the repulsion between the two negative species. Right, so it's time to do the actual Born-Haber cycle now, and it's of calcium oxide. They partially completed it for us, and we need to carry on. So let's have a look and see what we've got so far. Going down here, I've got the elements forming the compound, calcium oxide. So that's the formation of calcium oxide. I'm just going to put that on -635. We've then got atomization of calcium. I've got calcium solid becoming calcium gas. So atomization of calcium is 178. I've then got atomization of oxygen, half a mole of oxygen gas becoming a mole of oxygen atoms. So atomization of oxygen is going to be 248. Those of you who are bright-eyed will have noted that that is actually a typo on the paper. It should be gas. Right, and then it's up to us really. Let's ionize calcium first of all. So let's do the first ionization of calcium. That is going to be 590. Let's stick with calcium and do the second ionization energy of calcium. That is going to be 1150. I'm now going to do the first electron affinity of oxygen, which you'll notice is a negative figure. So that's -141. And I've still got calcium 2 plus in the gaseous stage. I've only got one electron because I formed O minus gas. Then I'm going to go to do the second electron affinity of oxygen to give me calcium 2 plus gas plus O2 minus gas, like so. And then obviously that guy there is delta H lattice enthalpy, and that number there, second electron affinity, is plus 791. Then all we have to do is put them into the equation for lattice enthalpy. So delta H lattice enthalpy is going to be -635 minus everything else. So 178 plus 248 plus 590 plus 1150 minus 141 141 plus 791. So that gives you minus 635 minus 2816, which gives me a grand total of minus 3451 kilojoules per mole. Okay, the next part is we're going to compare latency of calcium oxide and magnesium oxide. It told me they're different, so let's have a look. I've got magnesium oxide, Mg2 plus O2 minus, and calcium oxide. So the oxide ion is obviously the same. Charge on the cation is the same. However, the Mg2 plus ion is smaller and has a higher charge density than Ca2 plus. Therefore, Mg2 plus forms stronger ionic bonds with O2 minus and has a more exothermic lattice enthalpy. Right, so we'll move on to part D now, and it tells me, gives me an equation, gives me some data, and it wants me to calculate the standard enthalpy change for calcium oxide reduction from this equation. So the standard enthalpy change, so delta H is going to equal the sum of the formation of the products minus the reactants. So it's going to be, I've got calcium, which is obviously 0, carbon monoxide minus 110, and that's going to be minus carbon, which is going to be 0, minus 635. You've got a double minus there, so it becomes minus 110 plus 635, like so. And if we put that into our calculators, minus 1110 plus 635 gives us 525 kilojoules per mole. Okay, for the next one it wants me to calculate the standard enthalpy change. So standard enthalpy change is going to be the sum of the entropy of the products minus the sum of the entropy of the reactants. The products, so I've got calcium, which is 41.4 plus 197.6, and it's minus my reactants, which is 39.7 plus 5.7. If we do that, 41.7 plus 197.6, whoa, no, that's bonkers, isn't it? 41.4 plus 197.6 equals 239 minus 39.7 plus 5.7, which gives me 45.4. So let's do that. 239 minus 45.4, and that gives me 193.6 joules per Kelvin per mole. Okay, so we now need to calculate the minimum temperature at which this reaction is feasible. The minimum temperature, as we know, we go back to Gibbs fluidity, delta G equals delta H minus T delta S. If it's the minimum temperature, delta G is 0. Delta H we calculate as being 525 minus T, which we want to find out, times delta S. Be careful that this is in joules per Kelvin per mole, so I need to divide this by 1,000 to give me 0.193.9136, like so. So if I rearrange that, T is going to equal 525 divided by 0.1936. Let's pop that into our calculators. And that gives me 2712 Kelvin. Right, so we are carrying on now to question 5, and that is on standard electropotentials. So the first thing it wants me to do is electrical capacitance in all systems 1 and 2, write the half equation, so what's been oxidised, what's been reduced. So let's check out the standard electropotentials. This one is the most positive, it's minus 0.26, where this one is minus 0.44. So that's going to go that way, and that's going to go that way. Vanadium 3 plus is therefore being reduced because he's gaining an electron. So the reduction is V3 plus aqueous plus an electron becoming V2 plus aqueous. The oxidation is loss of electrons, which will be iron becoming iron 2 plus aqueous plus 2 electrons, like so. Right, so they now want me to determine the overall cell potential of that reaction. It's the difference between those two. So the difference between 0.44 and 0.26. Let's have a look. So is going to be 0.18 volts. So it's the difference between those two numbers there. So for the final part, it wants me to construct an equation for the two reactions based on 3 and 4. I've written those equations there so we can see them. This one is the most positive, so that's going to go that way. That one's going to be reversed, but steady on there. This has got 2 electrons, that's got 4. So I'm going to times this equation by 2. So that becomes 4H plus, that becomes 4 electrons, and that becomes 2H2. And now I'm going to pop them together. So this one's going that way, that one's going that way. So it becomes O2 plus 4H plus 2H2 goes to give me 4H plus 2H2O. And you'll notice that I've got 4H plus on both sides, so those two cancel out to give me O2 plus 2H2 goes to 2H2O. It then talks about what are the two advantages and disadvantages of doing this, using this rather than fossil fuels. Well, obviously one advantage is that I'm only producing water. I'm not producing carbon dioxide, which contributes to global warming. So that's a good thing. The other thing is that these are generally more efficient than using fossil fuel. Disadvantages, hydrogen gas, pretty difficult to store. You would have talked about how you store it as part of the course. And also, you've got to get your H2 from somewhere, haven't you? O2 you can get from the air, but H2 you've got to get it from somewhere, which could result, you could end up getting that perhaps from the electrolysis of water, which you've got to put energy in to do anyway.